Hi, hello. This is a topic two of the anatomy and the physiology. And okay, let me see. Let me set up a timer. Make sure I run finish in time. So the topic two is item and the radiation. So firstly, yeah. This is anatomy physiology, but why we start with item? So yeah, that's mostly because we have some basic knowledge about the fundamental chemistry and physics that we will use in our later class. And this is introduction of the atom and the ions and the protons, neutrons, electrons, and the radiation also. So let's start it. So what is an atom? In this, so far, according to physics, all the world is made of matter, force, and etc. So, but all the matters means all the things that take space, have mass, that's matter, and all matters is made of atoms. Then what is the atom? Atom is we can consider an atom is a small particle, and here we talk about the atom has two major parts: the nucleus and the electron cloud. In the nucleus, two type of say uh, particles, protons and neutrons. So let's say, let me see. Okay, so this is in the nucleus you have protons and neutrons, and inside the nucleus they are joined together, and each you see each protons is electrically charged with positive 1 electric charge, and it also has a mass of 1. And neutrons have no charge, that's like neutron. So no charge and have a mass of 1. And surrounding the neutrons, the nucleus, you have also electrons that make, and the electrons have, each electron has 1 negative charge, and we can consider no mass. It's not really no mass, but we can consider no mass at all for the electrons. So, and the number of electrons, also call it atomic number. And atomic number means each say atom has an atomic number, and then atomic number, the electron, the atoms have the same atomic number. We call them also the same elements. So why we call them same elements? And first, what is element? Elements is referred to some certain of pure substances. And how we define elements? Elements, all the elements have the same chemistry, same chemical properties. So which means the atom have the same atomic number, which means atom with the same number of protons have the same chemical property. And then why? That's because the number of protons determine the number of electrons. So, and then electrons give the feature of a chemistry, give an atom its chemistry properties. So, and why? Let's check out this. So here we got this one, the space. And then, so the electrons, let's move on to the electrons. The electrons is orbiting the nucleus. And this, in an atom, actually, the nucleus is very small. And the majority of space is occupied by electrons. But electron is even smaller. And actually, this is the majority of space is the space that electrons are running or orbiting the nucleus. And then the electrons orbit the nucleus not randomly. They orbit the nucleus in a special follow special rules. So surrounding this is the nucleus. Surrounding the nucleus, there are different shells. First shell, second shell, and third shell. There are more shells, but in today's class, we only talk about the third shells. And then on each of the shells, there are also, we call it orbitals. Shell and orbital. and orbitals. In the first shell, there's only one orbital, and each orbital can contain 2 electrons. So each orbital have 2 electrons. So in the first shell, shell 1, has one orbital which can contain 2 electrons. And then for shell 2, it has four orbitals. Each one contains 2, which means the shell 2 can contain 8 electrons. And orbital 3, a little bit different. Orbital 3 actually can contain more, but in this class, we don't talk about another 4 orbitals. So in shell 3, 4 orbitals. Each orbital have 2, another 8 electrons. So there's 3 shells surrounding the nucleus. And then when the electrons coming to fit into this atom, there are several routes. First route, they go to the lower shell first. They need to fill up the lower shell before you go to the higher shell. Lower shell first. And second, empty orbital first. So this is 2 routes, mainly 2 routes. For example, here, let's talk about different elements. So each element has a name. For example, hydrogen. I'm not hydrogen. Yes. I'm not sure you heard of hydrogen. Hydrogen is one of the elements, the smaller elements here, and each has a name and a symbol. Hydrogen is H, and the carbon C. Oxygen. I believe you have heard of oxygen, which is O, and nitrogen, which is N. So let's see how we fit the nucleus of hydrogen. Hydrogen's atomic number is 1. So it has 1 proton in the nucleus, and there's only 1 electron out there. It's on the first shell, this hydrogen. And carbon, I'm sorry, not. Okay, not for 6. Oh, 6. So I have 6 in the nucleus. So first 2 will fill the first shell, and then in the second shell, there are 4 electrons left. Oh yeah, I think I forgot one thing. Electrons first, and electrons at the beginning always has the same number as the protons, which means 6 protons, 6 electrons. And then the 2 electrons fill the shell 1, and then the 4 fill the shell 2. And when we fill the shell 2, it goes to the empty orbital first. If there are 4 orbitals in the shell 2, so there are 4 single electrons here. And these single electrons, we have a special name for it, call it valence electrons. So here in carbon, it has 4 valence electrons. And then let's say oxygen. Oxygen has 8 in the center. Again, fill the first shell, the shell 1 with 2 electrons, and then the second shell, 4 electrons will fill the second shell, 4 different empty orbitals first, and then there are 2 electrons left, and these 2 electrons will have to pair with one of the electrons. So which result in the shell 2 of the oxygen with 2 pairs here, 2 pairs of electrons and 2 valent electrons here. And for nitrogen, this may be homework. You can figure out nitrogen. That is say we call it electron configuration of the atom. And then why is important? Because here you can see this one. This is a pair. A paired up electron is very stable, and the valent electron is not stable. They always want to say find another electron to pair up. And this capability of finding another electron to pair up, this is the motivation of a chemical reaction. And for some of those electrons, or some of those items, let's say another one, call it sodium, or you say as Na. Sodium has 11 protons in the center, so this is 11. And then 11, there's 2 electrons in the first shell, and then another 8 in the second shell. Now we have totally 10. Lastly, there's a 1 electron in the shell 3. And then for all the atoms like sodium, which has only 1 or 2 or maximally 3 electrons, three single valent electrons in the outer shell, this electron was very easy to give up. In this case, because there's a single, you give up to someone else, to whom we'll talk about later. But this one will be given. We'll take it away by some other atoms, and then it results in like this: still 11 in the center, 2 in the shell 1, 8 in the shell 2, and no more. Now you see this is not balanced. Now you have 11 protons, which has positive 11 charge, and then you have 10 electrons, 11 protons, positive 11, 10 electrons, negative 10, which result in positive 1. Now this item is no longer neutral. It starts to have an electric charge, and this we call it ion. And here in this special case, it has positive charge. We call it cation. Cation is an ion, has a positive charge. And then this type of atoms that has, for example, like sodium and potassium, magnesium, calcium, all of those has only 1 or 2 or maximum 3 valent electron in the outer shell. This kind of atom, we'll call it metal atoms. And metal atoms, very easy, has high tendency to lose all the electrons in the outer shell and become a cation. And whenever in the solution, but water-based solution, this type of this metal is normally existing in the form of ion or cations that flow freely in the water. And then we have another type of electrons. Let's say take back. If you remember, this is oxygen. 2 electrons in the shell 1, 1, 2, 3, 4, 5, 6. This is oxygen. You see, this is the opposite of any of the of sodium or other metal atoms. It's only needed 2 more to fully fill the outer shell, and then in this case, the oxygen has a very strong power to acquire another electron and another 2 electrons to fully fill its second shell, its shell 2. And this, now you see it has positive 8 electric charge in the nucleus and minus and negative 10 in the electrons. Eventually it become have a negative charge of negative 2. In this case, here the oxygen now carrying a negative 2 charge. Actually, this is not a good example because oxygen rarely become this. Oxygen normally follow a covalent bonds with another one. Let's use another one. Okay, let's use another one. Let's talk about something else. What else? Say chloride. Now you heard this, Cl. Cl has 17 in the center. So in the first shell, 2. In the second shell, 8. In the third cell, oh, sorry, my drawing. 1, 2, 3, 4, 5, 7. So first cell 2, so we meet 2 plus 8 plus 7 equals to 17. It has 17 here. So in this case, it has very strong tendency to get another one to fully fill its shell 3. And then in this case, now we have positive 17 minus, now this one has 2 plus 8 is 18. Positive 17 minus 18 is negative 1. And this is another ion. It's another ion because now it has a negative charge. And this ion is called anion. Anion. It's a negative charge ion. So, and this thing, including chloride and oxygen, these two things, the capability of acquiring electrons, this capability we call it oxidization. Yes. And so this is the two poles of the atoms. Some of those is eager to give away its actual electrons, and some of it is to acquire. But there's also some other molecules and items, not molecules, items that kind of neutral. And okay, good. And one of those is hydrogen. Why am I doing? I cannot write. All right. Oh, technique issue. Why cannot write? Oh, yeah, that's why. Okay. Hydrogen. Hydrogen has only one in the nucleus, one proton in the nucleus, and one electron in the shell 1. So in this case, a hydrogen does not particularly eager to lose one or gain one, and rather it can share this one, which we'll talk about later. They share one electron with another called covalent bond. This is something in the next class. And then another thing is carbon, C, which has 6 proton in the center. But first, again, we have mentioned this, first cell 1 and second cell 4 singulars. And then these 4 singulars, normally carbon does not acquire or obtain any electrons from other atoms. It's only share those, which we'll talk about later. They're called covalent bonds. That's the thing we can in the next topic. So we're trying to say this is that not every single atoms kind of want to lose or acquire electrons. Some of those not losing, not acquiring in the center. Actually, most of those in the center, and to rather share with others the electrons. And then let's coming back. Let's coming back. Did I miss anything? Yeah, I may miss something, honestly. But again, prepare for the class. I'm sorry. For the class, please focus on this summary page. And then let's coming back here. Oh, what happened? Fix it. Coming back. Okay. Coming. Yes. Here. In here, you can see there's not only protons and neutrons. And then let's come back to talk about the neutrons. And neutrons, in most cases, they do not have a big influence on the chemistry property of the atoms. Neutrons. So, which means the atoms which carry the same number of protons but different number of neutrons are the same elements, but these call it isotope. in science, isos in many cases means equal. So they are same. For example, we just talk about carbon. We have example of hydrogen in my slides. Let's mainly focus on carbon. In the carbon, you can have 6 plus 6. That's the most common carbon. 6 protons and 6 neutrons. But 99% of carbon is this one. They call it C12. And some carbon have 6 plus 7. 6 protons, 7 neutrons, called C13. About 1% of the carbon is this. And then some of those have C6 and 8, called C14. C14, this is extremely low, and then this is unstable. These two, call it stable isotope. And this one, unstable. What do you mean by unstable? What are you going to do? An unstable C14 will automatically become N14. So at the beginning, if you look into my slides, I mentioned that elements stay as it is. Any chemical way cannot change one element to another element. That's a definition that proves itself, because whenever this kind of thing happens, one element becomes another element, this is no longer considered as a chemical reaction. This is called a nuclear reaction. A nuclear reaction normally rarely happens in our body. And however, it's not unrelated to life. Actually, this nuclear reaction is the basic is make every life possible on Earth. Why saying this? Because most of the life on Earth nowadays can survive because of solar energy, the shedding laws. And then this solar energy coming from the sun, from the sun. But how the sun gets its own energy? The sun gets its own energy because 2H, hydrogen, become a helium. Yes, I didn't mention this, helium. This is a noble gas. Noble gas means all of those elements by itself already fully fill all of those orbitals. So they are very stable. Mostly they stay in the one atom in the nature. When two hydrogen become a helium, not only changing the elements, but also it release a lot of energy. How is that? Energy. Yes. And this energy go all the way from the sun, reach Earth, and provide every energy we're now using on Earth. And what kind of things you can get from the sun? Most of the thing we get from the sun is the visible light. But what's the nature of light? The nature of light we also call it, no, not E, magnetic electroradiation. The sun is basically a radiation. Magnet and ER. I'm not sure. And let me take back my. I'm not sure my spelling is correct. Electromagnetic. That's right. So electric first. Yeah. Electromagnetic radiation, and then electromagnetic radiation. The nature of those is another particle. This is the last particle we're going to talk about today, photon. Photon is even smaller than the electron. In electron, we consider electron has no mass, but photon, is truly no mass at all. No mass at all. So photon, they can travel in any places, even in the vacuum places, in a wave. So photon travel in a wave. And then if photon, and say, there's two things can describe photons traveling: frequency or wavelength. In many cases, they are the two aspects of the same thing. The longer the wavelength, the shorter the longer the wavelength, the higher the frequency. The shorter the wavelength, the higher the frequency, the lower the frequency. So, and then if a photon travel in a very short wavelength and high frequency, this is blue. And the photon travel in a longer wavelength and lower frequency, this is red light to us. And then if the frequency is even, even shorter than the blue light, we cannot see it, but it exists. They call it UV light. And then if it's even longer than red, we cannot see it at all. Also, they call it infrared. So UV, and even above, like X-ray, gamma ray, all of those shorter wavelengths and high frequency are high energy. And then infrared, that's the perfect thing that for us to give. Not perfect. For us, this is the visible land from blue to red. We can see them, but infrared we can feel them as heat. But UV we cannot feel them, and above UV you can see X-ray, gamma ray. We cannot feel them, but it doesn't mean it do nothing. What UV can do to us? Damage DNA. They can damage DNA. So there are two ways it can damage DNA. Some of those light can break down the DNA directly. Some of those can generate ROS. Oh yeah, I don't remember I don't mention ROS. Please go read my summary. ROS means what is ROS? It's called also it's part of called free radical. A free radical. That means in most cases for any atoms that we can find, most of the items we can find here already pair up all of those electrons. But for ROS, for example, this is a hydrogen has 8. This is oxygen, 8 in the center. Again, this one and this one and this one. In many cases, in the regular oxygen gas, it has all filled up. But in some cases, they don't have one electron not filled up, and this one is very, very radically trying to kill or attack other molecules, and this can kill DNA. So that's the UV light, the X-ray has a strong power to damage our body. But that's something, and I'm not sure I mentioned in this class, pain, something we call it pain. Pain is our imagination. That's our sense to feel any of the harmful stimulus. But this is our pain is done by evolution. In the evolution, the harmful radiation does not always exist out there. So unfortunately, we did not evolve any sensor to feel radiation, harmful radiation, or we call it ionizing radiation. No, we don't feel it. We don't feel it as a pain. So when we have, say, UV light, X-ray, we don't feel anything. Although after that, those may kill some DNA, may damage some DNA in us. So that's and then why we don't feel it? Because that's another thing about it. This is Earth. I don't know how to draw Earth, whatever. And then this is solar light shining on us. Our Earth, we have an atmosphere here, and above the atmosphere, we have another magnetosphere here. It protects us from, it get away most of those radiation from the sun, the bad radiation from the sun. And our atmosphere also blocks many of those harmful radiation. So that means the Earth is ideal place for the life to exist. And then why we have this magnetic shield? That's because in the center of the Earth, there's a special thing, iron. In the center of the Earth, we have a liquid iron always circulating in the center of the Earth. And this circulating iron generates this magnetic field to shield us from the radiation. And in this whole universe, it's rarely find another place for life to exist. Have this perfect condition for life to survive. Okay, so that's all. That's all for the topic 2. Please keep in mind, in our second week, we have 2 topics. Later on, please find the topic 3, the molecules. Okay.